Okay, hello everybody, this is Jeff. And after the May 1st stream, the audience suggested that they would like me to do a kind of ground up C tutorial, not C++, C. And I was thinking about it during the stream and I thought, okay, well, you know, I tried to build Donkey Kong using Rust, and I got a fair amount of the way into that. Got graphics working, got tools built. So I thought, okay, if we're going to do a C tutorial, then let's try to build Donkey Kong again. Let's do it in C this time, and then I can actually compare and contrast for myself too, how that ends up. And I think I have an idea, but you know, then the audience can follow along. And I'm literally starting from main return 0. That's it. The only other pre-work I've done is I created my CMake project. I created the GitHub repository for CKong. I obviously CMake created, or I'm sorry, C-line created the main.c file and the CMake list text, and it created the build directory. I copied these find files for SDL2 from Ryu. So they just copied these in here. And then in my CMake list file, I just added a couple things, right? So I set the CMake module path to be the project source directory in the CMake folder. I added find package for SDL. So I've got SDL2, SDL image, and SDL TTF. Eventually we'll probably want to have sound. So eventually we'll come back in and we'll put sound in here, but we don't have that right now. And everything else was generated automatically by C-Lion when it generated the project. And all this code is going to be pushed into the repository. So ahead of the episodes or after the episodes, if you want to pull down the latest code and follow along, you can certainly do that. Okay, so it was suggested that I just do a basics intro before we really get into the project. So today, I think what I'm going to do is I'm going to try to cover the basics of C without getting too much into the project code, but at the same time, we'll write a little bit of project code. So we're just going to start off with the one file. We're not going to get too complicated to begin with. And as we get into adding files, I'll explain more about that when we get there. So the first thing I think we should probably talk about is just what you see in front of you, right? So what does this pound include? And we have angle brackets and we have this stdio, which people pronounce as standard IO .h. So what is standard IO.h? Well, C-Line will actually open that for me, and it's a header file. What's a header file? Okay, so we got to have a story here. So what's the story? The story is that a long time ago, back when the Earth was still roamed by dinosaurs and things were in black and white, we had computers that were very, very small. They were large physically, but they were small in terms of their horsepower and the amount of memory that they had. And because of this, writing something like the C compiler was quite a challenge, as you could probably imagine. And because of the limited memory, the creators of C were kind of clever at the time. They said, okay, well, we don't need to recompile, we don't need to absorb everything, all of the code files all the time. A lot of the times when we're compiling a module, a unit in C-speak is, so a unit is, a compilation unit is something that ends in .c. Okay, now that's, a lot of what I'm going to say is the general case. There are always exceptions, okay, but in the general case, a compilation unit is something that ends in .c. A header file is something that ends in .h. Again, there are exceptions, but don't worry about those. That's not really important right now. The idea back in the past was that you could put what were called declarations. which were simplified syntax. So examples here, you can ignore begin decals and end decals. These are macros. We'll get into macros. Same thing here. These are macros. We'll get into macros. But you can define things, and you're kind of telling the compiler about it. So as you can imagine here, you're telling the compiler that there's a function, and that it should expect that, and that when it sees it, this is what it should expect. Okay. And the header file was a way for them to accomplish a couple of goals. One, it was a way for them to kind of optimize around their low processing power and low memory capabilities at the time. It was also a way for them to kind of build, for the first time, the concept of shared code, shared libraries. So by having header files and having program A have a header file that program B could include, but not have to include the actual compilation units, that happened at link time. This created scenarios that didn't exist previously. So a header file, the way I think of a header file is this is where you put the headings, so to speak, of your code, but not the actual content within those chapters. Like the chapter, it's like a chapter headings, right? This is how you tell other parts of the system, here are the interesting bits about this thing over here, without the details actually being there. And so you'll find header files are very common. This is how the C compiler is able to know that there are these other things somewhere else that it doesn't have access to, but that it should consider. Okay, and as we're going to see soon here, everything is based on the type system, and the type system is actually very simple. So, and we're going to talk about that here in a minute, and the only thing you really have to remember is very much like an assembler, the C compiler has to know what the size of things are. And once it knows what the size of things are, and it has labels for them, it's able to allocate, it's able to arrange things properly and make sure that they're laid out correctly in the output that it creates, which is typically an object file of some format. And then later there's this thing called linker, which takes these object files, and the linker is able to get metadata out of these object files, and it's able to combine it all together. So when you have a compilation unit A, and you have a compilation unit B, A and B do not know about each other. So A.C and B.C are unaware that they cohabitate or that they could be combined. And it's through the fact that they can include header files that define the shape of things that later on the linker is able to take the output from the compiler, the object file, and turn that into something that actually runs. Okay, now the linking step is, there's complexity there, there's stuff that's going on. We're not going to get into those details until much later on, but just know that the C compiler is going to take your source code, your C file, it's going to include any header files, and it's going to emit an object file, and that object file has information in it in addition to the actual compiled code that allows the linker to later fix up all these things that we're missing. Okay, so now there's the C compiler, there's the C standard library, there's the C runtime. The C runtime you can think of as, it's just a library, and it includes some assembly code, essentially. Sometimes it's assembly plus C, sometimes it's just assembly, depends on the actual compiler platform and the target platform that you're going to be running on, that bootstraps your program, right? So the C runtime, you can think of it as it's the thing that gets your program going, and it deals with, for a particular platform that the C runtime is deployed to, it takes care of the nitty-gritty details of setting up a process and telling the operating system, hey, give me the command line parameters and all these complexities, right, that to get a program actually to the start line have to be done. And it would be kind of painful if every C program had to do that on their own. So the C runtime does that for you. Now you actually can compile C programs. They're called standalone, that don't have any runtime, don't have any library associated with them, and you have to build everything on your own. And in fact, I think this is what like Casey Moratori is doing in Handmade Hero, right? He's building standalone. He's building everything from the ground up. We're not going to be doing that, right? We're going to be using the standard library, the runtime, okay? So the runtime, the specification for C says that if you have a function called main, that when the runtime starts your program, it will call the main method, or the main function. Sorry, I get my terminology straight here. Main can be naked, meaning it doesn't take any parameters at all, or it can take parameters. So it can take the count of command line arguments and a pointer to an array of strings. This might seem complicated, but it's not. We're going to talk about this. And you might actually see this written a couple ways. You might see it like this. This is equivalent. Or you might see perhaps this, depending, right? Now, on Windows, there are differences here. I'm not going to go into those differences other than to say that there are a couple of different entry points for Windows. If you're doing Win32, you can have WinMain. If you're doing certain kinds of Unicode or wide character programs, you can have, I think the entry points are tmain. There's a couple different ones on Windows. Again, if you use Visual Studio, whatever boilerplate it generates for you, that's what you should be using. And just recognize that on Windows, you may have a slightly different entry point than on a non-Windows system. So I'm working on OS X. The code that I'm going to write will run on Windows, OS X, and Linux. But again, there are some variations there. So this is how the C runtime gets you the command line parameters. This includes the name of the executable. So the very first command line parameter is the actual program that you're running. And then, so the 0th entry is always the program you're running. And then 1 through n is any arguments that are passed. Now, you have to keep in mind that it's up to the shell, however your program is run. So if you're running it from bash, or if you're double clicking on an icon in Windows, it's up to the shell that is invoking the process to format the parameters to your program. So if the shell understands spaces for file names and things like that, the shell might automatically recognize a long file name and with spaces and combine them for you. If it doesn't do that, then you might have to quote them manually. So just keep in mind that there's a line between the shell, the thing that's going to maybe run your program, and your program itself. And you're going to be given a list of parameters based on how the shell interprets the values that are passed. And that's going to vary, is really the point that you have to keep in mind there. And of course, there are libraries that you can use, getopt being a very common one, that handle all those nasty details for you. But you may be surprised, right, to know how parameters are actually being passed to you may not match what you expect. So just keep that in mind. Maine has an integer, typically an integer return type, although I believe most C runtimes will allow you to do a void return for Maine. I don't recommend that. I recommend returning the int because this return value is what the shell, whatever invoked your program, this is what it's going to use to determine whether or not an error occurred. By Unix convention, 0 means all okay. Anything non-zero is an error. And there are some standards depending on POSIX about which error numbers you should use for what. We're not going to get into that because our program's not really, doesn't really deal in that domain. But if we were going to make a command line utility, we might spend some time to think about what kind of error codes we would return here so that a shell script, right, would be able to respond appropriately based on the kinds of return values that we provide. This is what's known as a function. You have your return type. You always have your return type. You have the name of your function. You have an opening parenthesis. If your function has no parameters, you have a closing parenthesis. You have an opening bracket, opening brace. The opening brace can appear on the same line. It can appear on its own line. It can appear tabbed. It can appear untabbed. It doesn't really matter what position the braces have. The intention of the braces was so that you could have a free-form format for your functions. You're going to see that my style is to just put the opening brace on the same line as the function prototype. That's what this is known as, the prototype. This is the block. This is a block. In compiler lingo, the thing inside of the braces is, you can think of it as a basic block. That's what the compiler refers to it as. You can refer to it as a scope. And we're going to talk more about scopes. Just know that each scope is unique, but it does include its parent scope. So that's something that you have to keep in mind. If your function is not of type void, return type of void, then you have to have a return. And the return type obviously has to match the type of the prototype. We're going to get into types here in a second. So this is your entry point. If we want to deal with command line parameters, this is the way we do that. So if I compile this now, that compiles. If I run it, it does nothing. It actually, on my computer, it takes a second to start because of the debugger. So you'll notice that the exit code is 0. If I change this to 1, now it's going to tell me that the exit code is 1 because that's what it returned. Okay, so that's, in this case, Maine is a special case. Maine interacts with the operating system. It interacts with the thing, the shell typically, in this case it's the debugger, that is running that process. So it's a special case. Now, return values work the same regardless of function, but in terms of the operating system, Maine is a special case. Okay, so now let's talk about types. We have int. This is a signed integer. Let's look this up, shall we? So, clang C11 int size. Typically, the int variable matches the word size of your platform. Okay. Now this is, you're going to see a lot of C code and a lot of C++ code that tries to avoid int like the plague. And there's a reason for that. A lot of that has to do with the fact that even though the standards say one thing, there's a lot of legacy code. And people, because I have to look it up, this doesn't really tell you how big it is, right? It could be 32-bit, it could be 64-bit. On this computer, it's 64-bit. But you have to be careful with that. What's signed? Well, signed means that it can be negative. And that's completely legitimate. Okay? Now, what if we wanted an unsigned number? What's unsigned? An unsigned integer cannot be negative. You can't do that. Notice that C11 highlighted this as a problem. Now, technically, I don't even know if the compiler, the compiler will take it, but this is going to generate a very large positive number, one that you won't expect, okay? So unsigned, no negatives. Signed, negatives. Now, here's the interesting part. So you have an 8-bit. So let's just go all the way up the chain. So you have 8-bit. Technically, you have 1-bit. 1-bit can be represented in a couple of ways. Typically, you pack 1-bit fields into an 8-bit value, so you could have a unsigned char, which is a byte, and you could pack a number of bits, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? 8 bits to a byte. You could pack as many bits into this as fit, okay? Another way you can do it is with a struct, and we'll talk about that in a little bit, but you can do bit fields in a struct. The thing that you have to remember is there is no intrinsic type bit. You have to represent bits within existing data types. And ultimately, that's because these map to registers in the CPU, and the CPU itself does not have something other than, it doesn't have a register that is sized of a bit. You have to deal with a register and then turn bits on or off within that register's size. So unsigned, so bits, and so, bits byte, right? So notice this is valid range is 0 to 255 because this is unsigned, okay? If we had a signed byte, the range is 0 to 120, negative 127 to, no, is that right? Negative 128 to 127, I believe, is the range. Let me just double check that. Yes, negative 128 to positive 127 is the range here, okay? So if we do signed char, I can do negative 112, and that's okay. That's a valid value. I could also do value 2 equal, let's do 77. Right? Those are both valid. Now, char is a kind of an interesting case. Char doubles as a byte, which is just a number, but it also can be text. So you can use a single quote and a valid character to assign to a char. And the compiler will recognize this and convert this into 65, right? Because that's what this is. Or, yeah, I think it's 65. My memory's horrible, as everybody knows. ASCII table, let me look that up. The letter A is 65. I got it right. So, okay. Now, just so you know, character does not necessarily equate to the number of things inside the quote, meaning this is considered one character, right? This is a null character. This is a carriage return. This is a line feed, right? Or the other way around. So even though there's a backslash in a character, that's still considered one character, okay? So keep that in mind. And that is a null, right? As represented by a character. But null is also that. They're just the same way of representing, different ways of representing the same thing. Okay. So then, sorry, I'm just jumping around the specification as we go through this. Okay, so then we have short. Which is a 16-bit value, right? These are 8-bit values. So an unsigned short is 0 to 65535. So this could be 32767, and that's okay. And we can also do 65535, okay? A signed short, which just doesn't have the unsigned in front of it, can be negative 32767 That seems wrong, the documentation. Oh, no, okay. No, that's right, never mind. So this can be negative 32767, and this can be 32767, right? So those are shorts. So 16-bit values, signed or unsigned. Then we have unsigned, I guess this is right. So unsigned by itself or unsigned int. These are the same thing. Okay, so you will see occasionally some C code that just uses the word unsigned. Right, can be 65535, or you can do it unsigned int, right, like that. Okay, and then signed int is the same as yeah, see, the spec is so strange because it's everything is defined as minimal. So what the actual range is compiler or platform dependent, but these are the minimums, right? So an unsigned int, oops, I'm sorry, a signed int, my bad. So it's either int, signed int, or signed. Those are all valid for the same thing. Then this is the same basically, minimally, as a short. And we can just, compile that to be sure. And then you have long, And we're going to see here in a second why this is why things like C standard types and things like that exist, because like uint32 and all that stuff, because this gets really confusing really fast. The standard types in the language are very, no one uses these directly typically. You'll see old code that tends to use these, but so a standard signed long, it can be up to, so this is, the minimum is 32 bits, right? So a signed long can be -21474836447, and the unsigned version, or the positive, sorry, long positive long can be 21474836447. And then there's long, which is what we would consider a 64-bit value, right? And this is massive. This is a huge number. This is like, yeah, huge number, right? Just suffice it to say, you can have these, right? And they're big, very big. The chances of overflowing those are pretty minimal. Then you have floats. These are single precision floating point. And again, these have a very broad range of values. Then you have double, which is double precision floating point. Right. And then you have a long double according to the standard, which is an IEEE 754 quadruple precision. So long double, quadruple precision floating point. No idea, right? Some really big number. Crazy. So, okay, so these are your default types. We haven't talked about pointers yet. We're going to talk about pointers in a second. But just understand that these are the base types in C. They're all numeric. Even char is numeric. Don't confuse the fact that you can assign a character to it as a string. It's not a string. It is a number. They're all numeric types. The compiler is taking this and converting it into a number for you. It's just a convenience thing that you can use this representation here, okay? And pointers, the key thing to remember, oh, we didn't talk about void, so you can do void. But void can only be used in two ways, as a return type or as a pointer type. Okay? So we're going to come back to that because we're going to talk about pointers in a second. But any one of these could be a pointer type. A pointer is something that you add to a base type, telling the compiler that the size of the thing that you're pointing to is this type, which is why you will typically see char star. Why? Because this is a byte pointer. Because you typically, not always, but you typically want to access memory a byte at a time. So you will tend to see char star or char star, however you say it. It does not matter if the star goes with the type or it goes with the variable name. That's just a style thing. You can, or you'll see code that looks like this. They're all equivalent. It makes no difference. I personally prefer binding the manipulator to the type because that's technically what's happening, right? You're modifying the type, not the variable, but that's your, however you want to do that is completely up to you. This is the style you'll see me use. If you wanted to index memory by 16-bit increments, then you could make a pointer like this, right? And that would be legitimate, right? Now we have a 16-bit unsigned pointer that we could use. So this part is just telling the C compiler this pointer, when you add to it, when you add 1 to the pointer, you're actually adding 16 bits. You're adding 2 bytes. If I were to put a pointer on, if I were to put a pointer on this long here, which is a 32-bit, this pointer would, every time you add to this pointer, add 1, it's actually changing the pointer by 4 bytes because that's the size of a 32-bit number in memory. Okay, so that's why the pointer type is attached, why the pointer is attached to the type. Because what you're telling the compiler is this pointer is this size, and when you do a pointer arithmetic with it, that's what you get. Likewise, when you dereference a byte pointer, you get a byte. If you dereference a short, you get 2 bytes. And if you dereference a 32-bit value, you get 4 bytes. And if you dereference a 64-bit value, you get 8 bytes. Okay? So, now again, these are all minimum sizes, not necessarily the sizes that a particular platform is going to use. Yeah, so fixed width integer types. Yes, this is C standard. C standard int is the C++ version. Standard int is the C version. So we're going to pound include standard int. Okay, so now if we look at standard int, it's just another source file. You can look at them and you can see most of your tools nowadays will know like which preprocessor flags are being used. So you can see what parts of the include files are active, right? And so then you can see how they type def these. We haven't talked about type def, but you can just think of type def as alias. It's just a way of creating an alias. We'll talk about this, right? But this is much more logical, these sizes, than the standard ones that are built in. I highly, other than char and void, I highly recommend you avoid using the base types. They're confusing. Char, void, float, and double. Those probably would be the only base types I would use. Everything else for integers, I would use these types, right? So sint, just int 8t, right? So this is a signed char, uint 8t, unsigned char, int 16t, signed short, uint 16t, unsigned short, int 32t, signed int or signed 4 byte, depending on how you want to look at it. And this is uint 32, or I'm sorry, int 32 min. And then uint 32t is unsigned 4 byte. This is uint 32 max. And then you have int 64t, signed 8 byte, int 64 min, and then uint 64t unsigned 8 byte, uint 64 max. And then float, yeah, see, float and double, they're just, you can just use float and double as is. I don't think there's really any particular single, double, right? And then void, and we're going to talk more about void and pointers and things. But for integer types, this is what I'm going to be using. This comes from that standard int. And again, what you have to understand here is the first set of types we went through, that's what's built into the compiler. This is a type def, okay? This is a typed signed char, a type def signed char. So this is actually what the compiler sees. This is what we're using as the alias, okay? Because it makes more sense. It's cleaner. If we look at the unsigned uint 8t, right, it's an unsigned char. If we look at the int 16t, oops, I keep hitting Control V, it's a short. See, and this is where it gets confusing, right? Because remember, short, the minimum size was 16 bits, right? An unsigned short, an int, so see, this is a 32-bit value according to the Apple platform, right? This is a 32-bit value. So this is why these types exist, these type defs exist, because you can't, unless you do some preprocessor magic, you can't know for certain how the default C types map to a particular platform. So it's much, much safer to use these type defs because there's header files that take care of all that for you. And then this is probably a long, I'm guessing this is just a long, well, this is actually a long. So not just a long, it's a long. This is an unsigned long, right? So yeah. So anyway, those are our types. That's it, right? Notice there is no string type in C. And you're going to say, oh, but C has strings. No, it doesn't. It has memory blobs that act like strings. There are library functions that will treat a range of bytes in memory that have a 0 at the end as a string. But there is no string type in C. And we're actually going to make our own string type for our project because the standard C string type sucks. I don't like using them. So those are types, okay? Now we're going to come back to these a lot, so don't fret. Now, why use this here if I say, use these other type defs? The only reason that I would stick with this convention here, although you are going to see this, like I say, potentially coded a couple different ways, depending on platform, depending on compiler, is this is just typically what you see in the main signature, in the main prototype. It doesn't, there's probably, for each platform, a really accurate prototype that's like the most correct in terms of its definition. However, by convention, I always have just kept my main method looking like the main methods that you would typically see for platform-generated code. So this is, and again, char is one of those things that I will typically use straight for pointers. Although, I typically will do like a uint 8t char or star instead of a char just because I think it's more descriptive. Because char, again, it just, C is old, right? So just remember that a lot of the names that were chosen here, they made sense at the time, but they're confusing, right? They should have called this byte. They didn't. But hey, it is what it is. So, functions. Now let's do some simple stuff, okay? Let's talk about struct. Now in C, structs are anonymous unless you, well, okay, I'll explain it both ways. It's probably easiest that way. So let's create a struct and let's call it a p string t. Actually, let's call this p string. Sorry, because I gotta remember I gotta do type def. So I'm remembering my my C anyway here. So actually let's just call it string. That's the tag, okay? And we're gonna put a unt in here for the length, and we're going to put a unt8t pointer for the data, okay? How many bytes is this? What's the size of this? So this is a byte. This is not a byte, right? It's misleading. This is the size of a pointer on the platform, which in this case would be 8 bytes. It's a 64-bit platform. So even though the size of the data is a byte, it's still a pointer. So it has to be able to point anywhere in address space to access data, okay? However, when you dereference this pointer, the size of the dereferenced element, or when you add to this pointer, the amount at which the address changes is dictated by the size of the data type for the pointer, okay? Now, to use this struct in C, with the way I have it typed here, I have to use the struct keyword, okay? If I don't do that, if I take the struct keyword out, I get an error. Let's see what C11 says. Yes, see, C11 says you need a struct here. Why? Okay, so this is just the syntax, how C does structs. This is a what you would call a, I guess, an anonymous struct. It's not really the right term. I'd have to look in the spec again. But this name has no global applicability to it. It only is applicable if the struct keyword is included. Now you will see code, some C code, especially like the Linux kernel, I think, follows this convention. There's quite a bit of code, C code, that follows this convention. I don't personally, I use type defs, but this is not uncommon, okay? And of course, now I have this struct, I can set data to be something, right? And length is 32. I don't know. So just as an example, okay. Now I don't know why it included m hash, and that doesn't seem right. Why does it keep doing that? M hash. Yeah, that's not the right header file. I think this is an issue. Yeah, this is an issue with client. So standard lib is the include file that it should have picked to include malloc and free. You can also, I think malloc.h is a valid option here, okay? Now, I'm just doing this for an example. We're gonna do this right. But I wanted to point out the fact that a struct, without it being wrapped in a type def, requires the struct keyword. And that includes anywhere where the struct would be referenced. So if I had a function that accepted a pointer to a string struct, this is the way it would have to be written, okay? So just keep that in mind. Now the way to not have to do that is to use typedef. So that's typically what I would do. So this is the name of the struct. This is the name of the typedef. Okay? Because if you'll remember from our other examples, this is what the other typedef line looked like, right? Original type, alias name. But with the struct, you want to make it kind of look nice, right? You want it to fit in. So because C is freeform, you can do that. Line breaks don't matter. This works just fine, okay? So now I can do string t test. Then test data is uint8t malloc 32 test length 32, right? And that is equivalent without needing the struct, okay? So, very important point. So now what we're going to do is, if we wanted to create strings, let's say we want to have a little library. We don't want to use the C string stuff. It's nasty. We want to use length prefixed strings. So let's actually go all out here. Let's make this a 16-bit number. So we can have strings that are up to 64K in length. That's a pretty good size. And 64K should be enough for anybody. That's my Bill Gates thing there. So let's now write a couple of helper functions. So this is very common in C. So string t pointer, let's call it string new, and you can pass in a const char star stir. Okay. Now, so here's where I'm going to cheat a little bit, just a wee bit, and I'm going to use the standard string library just at the beginning to create the string. This is a convenience thing, and we're going to have a couple of these so we don't have to do this all the time, right? So how do we do this? We said string p string, and actually, yes, this is correct. So what we want to do is we want to allocate this. So what we have to do is size of string t, all right? And we have to cast this because malloc returns a void pointer, right? So we need to cast it to the type that we have. Is this null? And if it's null, we want to panic, right? So let me see here. C panic. Trying to find the right. Yeah, okay, yeah, let's do it that way. Right, so then string dot data is going to be, I'm sorry, not dot, string arrow data is going to be stirdup, stir, and string length is going to be stirlen, stir. And it wants cast because I'm using these specific types which the library doesn't deal in, right? This is probably returning a size t, and this is returning a char star. Yep. So, all right, so we're going to return string. Okay? So let's look at this. We have a function. It's a global function, and it's called string new. We can pass in an existing const. So the reason I made this const is because this is really for inside the compiler, right? So my intention here is at some point we're going to have strings like this, string t, hello world, and we're going to call string new hello world, right? This, the compiler converts this into a const char star, and this is null terminated by the compiler by convention. So we can create our length prefixed string, our wide string, whatever you want to call it, by passing that in and using the library in this one spot to convert it into something that's sane, right? And then we can say actually, let's not do it that way. Not yet. Let's look at it in the compiler or in the debugger instead. That's a better way to do it. Okay. So hello world is an allocated, it's allocated on the heap. It's our string t, okay? We look inside of it, it has a length of 12. There's our data. Boom. Okay? Length is 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There you go. So perfect. All right. Now, I just leaked memory. That's okay. The operating system will clean that up in this case, but we want to behave, right? So we need to create a free function. And this is going to take a string t and we're going to guard here. So if string is null, return, otherwise free string. Okay? So free hello world. Oh, I'm sorry, not free. String free hello world. Now, there's another leak here. I don't know if you noticed it. The other leak is the data. Because if we look at stirdup, what is stirdup doing? Stirdup is duplicating that string. It's allocating another buffer and it's copying the bytes into that buffer. We're just getting the pointer to that buffer. So when we're done with it here, we have to clean it up. And that's going to be true whether we do stirdup or we have our own string new. So let's call this one string clone, because that's kind of what it's doing. Let's create another one called string new, and we're going to call this one, or we're going to have a parameter passed to this one of uint16t length. okay? And we always want to check malloc, the result of malloc. If it's null, we want to bail, because that's bad. If we can't get memory, we're done. So now we're going to do a malloc ourselves here. And since it's bytes, we don't have to do anything special. We don't have to take the size of anything. We just call malloc and pass len. And that's how many bytes we're going to get. And then the length on the structure is len. And we return the pointer. Okay? Now, the same free works for both. So we allocate string, or we call string clone, passing in a C standard, or a C string, a zero terminated string, and we convert that into our structure, our length defined structure. And then when we're done with it, we free it. Now, what if we want to print it? Actually, let's be consistent. We'll pass the string first and the file pointer second. Okay, so there's a function called fprintf. Okay, takes a file pointer, and then it takes a const char star. Now we don't have a const char star, so we have to do something special. We have to add the 0 onto the end here. So how are we going to do that? Well, there's a couple ways we can do this. None of them are particularly appealing in C. This is why things like, again, this is kind of like assembly language, right? So what would we do in assembly language if we were doing this? Well, one thing we could do is we could just have a fixed buffer, right? That's of some size. Now we know that the maximum size of our string is 64K. If this were single-threaded code, which it is, we could make this static. So there's one static 64K buffer for every call to string print. But this is a decision, right? This is not thread safe. Now, if we were going to do threading, we could cheat. We could move this buffer to thread local storage. So for every thread, there would be a buffer, a 64K buffer, for string print that's thread safe. So string print would look at thread local storage, it would get the buffer, and it would use that. Since we're not doing threading right now, we know we're not doing threading, this is okay. We can have one 64K buffer because that's the maximum size of our strings. And it actually allocated one, we should allocate one byte above that because we have to put the null on there. So what we're going to do is we're going to do a mem copy from string, or I'm sorry, this is destination. So we have to take the address of the buffer, and we're gonna talk about this in a second, and the source, which in our case is the data pointer on the string, and we already know what the length is, okay? And then we're going to set at the very end of the buffer for the length of the string, we're going to set that to 0. Now, there's typically in C code, you probably would see this because people would want to kind of sort of document that they're adding an ASCII 0 onto the end. But either way works, it doesn't matter, 0, 0, okay? So fprintf takes a destination file, and it takes a const char star. So there you go. Now, what we should do is if string, actually we should probably just do assert here. So assert string not null. Assert file not null. Right? This should not happen. I would say we could do the same thing here. This, yeah, whether this should be an assert or a runtime check is kind of an interesting question. I mean, they're both runtime checks, but the if statement wouldn't fail, right? In this case, if data is if data is null, the program's going to end. But I would kind of argue that that's probably what we want in these cases, right? We're trying to catch bad code, and once that code's fixed at runtime, this shouldn't happen anymore. Now, asserts have overhead to them, so ideally at some point you'd if-def this stuff out. But again, I'm probably getting way ahead of myself here. So we clone a string. We're going to call string print, and we're going to pass standard. How was it? C. There's a. Oh, what is it? There's a file pointer already for us. Fprintf standard out. Always forget. And there's a reason I'm using fprintf, which we'll get to here in a minute. Oh yeah, it is just standard out. Right, it's a macro. But this is the string. So hello world standard out. So here's the reason why I wrote string print to use fprintf, because not only can we write to standard out, standard error, but we can also write to files now. So if we open a file, we can actually use this existing string functionality, and it will work with files right away. So let's compile it. Okay. Not a string literal. Need to take the address of. Oh, did I forget the format? I think I did. Yep. Sorry. Oops. There you go. Okay. So then if I run this, hello world. Okay. Now let's step through it. Okay, so first, we're going to clone the null terminated C string. So we allocate our structure in memory. If that's null, something bad happened, we bail. But that's not the case, we're okay. So then we use the strdup. So strdup and strlen, these are part of the standard C library string functionality. But we're only going to use these in this one spot up front to clone existing C strings. We're not going to use them anytime after that. Okay, we're going to do our own thing. So we copy the content of the string, strdup, into our data field. Strdup, and I just know this from memory, strdup allocates memory. So one of the things that you have to be very aware of in C, it's kind of the convention, is you have to look at functions, and they will typically, like in the man page or in your documentation, they will say, strdup allocates, you're responsible for freeing. Or the pointer you pass in gets assigned allocated memory, blah, blah, blah. So then you're responsible for freeing it. So ownership is kind of defined in the documentation, not in the code. Then we set the length using strlen because, again, we got a C string that came in, so it has a 0 on the end. So strlen can find the length by walking the bytes and seeing the 0 and saying, oh, it's 12 bytes long. Then we return the pointer back out. So now we have our string T structure, a pointer to 1 on the heap, and it has the cloned data in it. So if we look at the hello world variable, the length is 12, and our buffer points at this string, hello world. Okay? And then we want to print it. So we go to string print. We pass in the pointer to our string structure. We assert that it's not null. We assert the file handle that we passed in is not null. we have this static buffer. This is our static work buffer, because what we have to do is we have to take our string data, which doesn't have a 0 on the end, we have to put it somewhere, and then we have to put a 0 at the end in order for fprintf to deal with it. Now, there's actually a way that we could kind of sort of cheat slightly. I just thought of that. We could put the /0 in the literal for fprintf. I didn't think of that. Maybe we'll try that. So, and then let fprintf deal with the buffering. We'll try that. So we do the mem copy. So we're going to copy our bytes from our data buffer with our length into our work buffer. So if we look at buffer here, right, we have a 64K plus 1. So it's all zeros. The compiler conveniently initialized it for us. And we're going to do the mem copy. So boom, there's the mem copy, HELLO space, and then world, bang. Now, because it had already allocated this with zeros, we can't really quite tell, right? But we're going to put the 0 on the end. And then we're going to print it. And that's it. And then we free the memory. Okay, so now we could, I just thought of this, we could kind of cheat. We could do this. Not really cheating, it's just being really clever, right? Our data doesn't have a 0 on it, but we know that it needs a 0 in order to, oh, but yeah, see, that won't work. I just realized that. Because it's going to walk this memory buffer until it finds a 0, but there's nothing there. So yeah, that won't work. So what I was doing was right. Unfortunately, that's all we got. So what we could do, what could we do? We'll leave that. We'll leave it that way for now. It works, right? This gets allocated once. It's static. And we just keep reusing that buffer over and over and over again. And then if we did want to go threaded, we would put that buffer on thread local storage and do the same thing, and it would be fine. Now, we need a couple other things here. uint16t string length. We pass in a string pointer. And again, we just want to assert that it's not null. And we want to return string len. There you go. Now technically, you could get the length off of the structure, the pointer, if you wanted to. But just for the sake of completeness, I'll create a little helper function to do that. Okay. So now hopefully that makes some sense. We talked about the base types in the C compiler. We talked about the main method. We talked about the standard int header file, which has some really nice, oops. Sorry, CLion doesn't pick the right header files. So we talked about standard int, which has the uint 8t, 16t, and all the int sizes. After we looked at the base types, standard lib has malloc free and a bunch of other stuff in it. String has the stir dupe, stirling, stir copy, all that good stuff. Assert has the assert macro in it. Standard IO has file stuff in it and other fprintf, printf, a bunch of other stuff. We created a struct. We talked about structs with and without a type def and what the difference there is. We have our string structure because having a length prefix string is far nicer than doing what C does. And what C does is it puts a 0 at the end of the string, and then it literally all the standard C string functions, they walk byte for byte till the end and they see a 0. And this is, when people talk about the dangers of C and bad things happening in C, I mean, I personally think a lot of that stuff can be, traced back to people using C strings. And as you can see, I mean, for basic stuff, right? We can clone a C string. We can create a new one of our strings. We can free a string. We can get the length of a string. You know, and obviously, like, appending strings here would be very easy. If we had 2 strings, we would just allocate a new string. We would copy the data of one into the string, the new string, copy the data of the other into it. After we'd allocated, so actually let's do that. Let's do string t star, string, concat, string t, left-hand side, string t, right-hand side. Right? So how would we do this? First, let's assert that the parameters that were passed in were valid. Then let's allocate a new structure. So it's size of string t times 2. Oh no, sorry. We're just going to allocate one new of these. And then the data, sorry, is going to be uint 8t star malloc left-hand side length plus right-hand side length. Right? Because we're going to concatenate the 2 strings together. And then length is just left-hand side length plus right-hand side length. Then we're going to do a mem copy. The destination is string data. The source is left-hand side data. And the length is left-hand side length. And mem copy string data plus left-hand side length, right-hand side data, right-hand side length. That's it. Then, so now the question is, okay, if we concatenate 2 strings, do we want to free the original 2 strings? Or, you know, like, who owns those? I would say in this case, we don't want to change the ones we pass in, right? We just want to read from them. So we can maybe make them const here. And then we return our newly allocated string. And you could imagine, like, okay, here's another one. String left. Const string t string. Okay. Or actually, we'll just call this left-hand side. So we're going to assert that it's valid. We're going to allocate a new string. And the data is going to be we're going to allocate a data buffer that's the size of the length we're trying to get. Right? So left is classically the string. You say left string, comma, 5. So if the string is 10 characters long, you get the 0 to 5. Right? So what we want to do also is we want to assert that length is greater than 0 and length is less than left-hand side length. Less than or equal to, right? And so length is going to be the length that's passed in. And then we're going to do a mem copy. The destination is our new string buffer. Our source is left-hand side data. And the size is length. And we return that new string. Right? So we have hello world. We print that. Then we have hello, string left, hello world, comma, 1, 2, 3, 4, 5, string print, hello, to standard out. And then we want to free, string free, hello, and then string free hello world. And actually, no, yeah, that's beautiful. Do that. Boom. Now, what if we wanted to put a new line in between there? So we just put a new line There you go. Hello, hello, hello world, hello. So, and so you could see very trivially, right? We can build a string library. And, you know, I've been doing this about an hour and 20 minutes. And that includes me, you know, taking time to explain some stuff. So, you know, it's not complicated. So let's do string right while we're in here. And then we're going to do one more refactor, we're going to do one more step to kind of introduce modules and static and things like that and header files. And then I think for this first, you know, session, we'll cut it there. And then we'll, you know, in the next one, because we're going to use this string stuff, right? This is good. All right. So write, typically, the write function is usually write foo2, which would be equal to oo, right? This would be left foo, or left hello world 5 equals hello. This would be concat hello space world equals hello world. This would be hello equals 5. So, right, we want to make sure the parameter we pass in is good. Length has to be greater than 0, and length has to be less than or equal to the total length of the string. We're going to allocate the new string. This is almost exactly the same as left. The only difference is here is how we index into the pointer. So the source, or I'm sorry, the destination is the same, but the source is different. So here we, so this actually is an interesting one because we can't really do a memcopy because memcopy won't go backwards. So here we can actually do some, fun stuff. Uint 8t p is equal to left-hand side data plus length, right? Because what we want to do, we're going to copy from the right. Oh, sorry. Left-hand side data minus length. So, because we want to copy, yes. So, oh, you know what? Sorry. I can use memcopy. We're going to put it in data. It's going to be left-hand side data minus length. And then it's going to be left-hand side length minus length. Yes. Return string. Sorry. So the pointer, data points at the beginning of the string. Plus left-hand side length minus the length that we pass in. So we're gonna scooch the pointer all the way to the end of the string. We're gonna subtract how many characters on the right-hand side we want to get. Okay. And then we're going to copy the number of characters that we want, and that's it. So world is 5, we have the bang. So 6 characters, right? So string t world bang is string right hello world 6. String print world bang standard out. String free world bang. I'm off by 1. I'm off by 1. Imagine that. So I'm still going to be off by 1, but... All right, so let's look at my math here. So this points at H. This pointer here points at H for the hello. The length, in this case, is going to be 12. Right. I'm 1 off. I'm always 1 off. There you go. So, there you go. We've got a string library where we can clone a string, clone a C string. We could create a new string for a length. Now, we don't have a way of putting things into that string yet. We'll do that. We need to add that. We can free a string. We can get the length of a string. We can concatenate 2 strings. We can get the left-hand side of a string for a length. We can get the right-hand side of a string for length. And now obviously doing an arbitrary substring where it's start length or start and end, we could do that very trivially. But what I wanted to do next, oh, and then we can print the string, right? So what I wanted to do next was, let's go through and create a module. So we're going to create a C source file and header combo. And we're just going to call it string. Make sure, put it in there. And then we need a header file too. And you can ignore the Ryu header. I have C11, it just configured to, oops, you put it in the wrong spot. Okay. All right, so then what we're going to do is, oh, I want to call it string. So we don't conflict with the existing, I'm going to rename it to stir. And, you know, let's rename our type to stir t, and that way we won't conflict with string.h. Not that I think that would be a particularly big deal, but just to be on the safe side. Naming things is hard. It's always hard. Okay, I'm going to rename the functions too, just to be consistent. And just to kind of round some of these out, so we call get the length, and let's also call struct and cat and pass hello and world bang, and we're going to print those two. Ooh, that's interesting. Malloc, left hand length plus right hand length. Length is left plus right. Turn stir. Okay, let's figure out why that isn't working. So we allocate a new stir t. We allocate a new buffer, the length. So stir length is 10, which is correct, right? World and hello, yeah. So there's world. Oh, world. Oops. Wait. No. No, that's not right. Oh, see? Here's where you get in trouble. I freed world bang, so I was running off with a bad pointer. That's what happens. So let's actually, I'm going to move all the frees to the end here. See, this is where, like Jonathan Blow has that, he used that defer keyword in J. This is where defer would be awesome, right? Because what you could do is say defer, free, defer, free, defer, free, and then it doesn't actually happen until down here, right? Where you want it to happen, and then you avoid what just happened to me, right? So, you know, those are little things, right, that would make, there you go. Now you get hello world again. Okay, so now we're testing all of our functions, all that works. So here's what we're gonna do. We're gonna take all the string stuff, and we're gonna copy it, and we're going to move it to stir.c. And we're going to move our struct to the header file. And I'm going to talk about the brackets versus the quotes and all that here in a minute. Okay, so now we need to prototype this in our header file. So I'm just going to be really lazy. I'm going to copy all the code, and then I'm just going to get rid of it. So here are our prototypes for our functions. Now, let me look at, there was a good example on one of these. Oh, let's look at stirdup, maybe. Yes. So stirdup, no, actually these aren't good examples. Some of them, you will notice that they don't include names in the prototypes. So this is a completely legitimate prototype because the compiler doesn't care at this point it doesn't care what the variable's named. It's not relevant, okay? The only thing that really matters at this point is what the type is, and that type conforms to the type of the function that's actually in the compilation unit that's going to get linked. So you will see code like that. So just remember that you don't have to have names in your prototypes. Now, again, is that good form or bad form? I mean, I'd be inclined to say nowadays it's bad form because there's really no overhead or cost in including the variable name here. But again, you know, it's just something to keep in mind. Now, quotes versus brackets. The primary, again, this is implementation dependent. So if you read about your compiler, what it will tell you is, you know, or read the standard, it will tell you quotes are up to the compiler. But in general, what happens is your current directory or your project directory path is consulted first for includes that are quoted. For includes that use the angle brackets, the system include path is consulted first. Now, if you look at like how I did Ryu, I include my project path in the system include path, and I do that for a couple of reasons. So you can go either way with it, but typically quoted includes are meant for things that are inside of the current folder, inside the current project path, or relative to the compilation unit, I guess would be another way of looking at it, right? This is a peer to the compilation unit, so the quoted include will find it there first. So now in Maine, we're missing all this stuff. So we include stir.h. We compile, voila. 2 compilation units, 2 object files, executable, and the runtime behavior should be identical, right? But what did we just do? We just took all of our string stuff and put it into a module. You could take this C file, that header file, and you could copy this into any other project you want, and as long as you put it into your make process, you know, so that it gets compiled and it gets linked, you're done, right? Away you go. Now, what if we wanted to have private behavior specifically to this module? So as an example, let's talk about this buffer. So it's static. So we can move that now to the file level of the stir.c compilation unit because it's static. So this is, you can think of static kind of as private to a module. And so again, behaviorally, this code is going to work exactly the way it did before. But instead of it being inside of that function, this is now at the module level. And other parts of the code can't see that, right? Only code inside of this module can see this. Now, what if you wanted to write a function that was a helper function for these other functions? Well, you wanted it to be private. You didn't want to share it with other parts of the code. I mean, there's a couple things you could do. You could make it global and just not include it in the header file. That's one way. Or you could make it static, which is typically what you would do. So your public interfaces in C on a module are going to be your global functions that get included into your header file, right? These are things that the rest of the world sees. So again, when main.c gets compiled, main.c includes stir.h, and the compiler sees these prototypes. That tells the compiler what the shape of this code is, And then the compiler's fine. The compiler's like, oh, okay, I know how to figure this out. I'm good. I know how big the structure is. I know what types these functions expect. I know exactly how to do this. And then when the linker runs, the linker opens up stir.c.o and main.c.o, and it fixes up. It links those things together so that this code actually, in fact, calls that other code. And it changes, addresses and, redefines things so that they can be combined. Now that's static linkage. Things like dynamic linkage, like shared libraries and stuff, that starts to get slightly more complicated. Again, the linker takes care of the majority of that, but it's just something to keep in mind. Okay, so I did a lot of stuff on the string stuff, just kind of based on the really basics that we talked about at the beginning. I'm sure you guys will have questions and you want me to focus on specific areas. We can probably do follow-ups in the stream, or you can tell me areas that you still have questions on or you think I should spend more time with. But what I'm going to probably plan to do is each day I will make one of these videos and I will just start slowly building up functionality towards the game, towards Donkey Kong, and going in this route, right? So we've got some string support, then we're going to do some, support for state machines, and we're just going to slowly build some stuff up, and we'll get slightly more complex as we go. But the building blocks, and this is the critical thing I want to mention here, believe it or not, we've covered almost all of the building blocks at this point. We've done header files, we've done modules, we've done globals, we've got static, right? We've talked about all the types, we've talked about type def, we've done a struct, we've done pointers. So believe it or not, for C, now of course there's always esoteria, right? There's always corner areas of stuff that you don't tread very frequently. But for what we're going to be doing, and for a lot of what you will do in C, believe it or not, here it is, right? This is it. I do want to mention a couple things. One, I am using the pragma once directive because it works. Now, there are cases, so what does pragma once do? In a header file, right, the C compiler is stupid. It doesn't keep track of what's been pound included. So if you tell it to pound include the same thing over and over and over and over again, it will gladly do it. It doesn't have any rules, right, around scoping things at that level. However, you can control that. So pragma once tells the compiler, hey, keep track of this. You've included it. Don't include it again. This is what I would consider the modern way of doing this. Now, there are some cases where pragma once is not the correct thing to use. The old-fashioned way of doing this is to use a pound define. So if not defined, this is the preprocessor now. We haven't talked about that a lot yet. But if not defined, stir H, and it doesn't really matter what you call the macro. It keeps trying to help me. Don't help me. Pound define, stir H, okay? Then down here and define. So what is this doing? This is saying to the preprocessor, the C preprocessor, is the symbol underscore stir underscore H defined? It won't be defined until the first time this is included per compilation unit, okay? Once it hits this, it will then define it. Once it's defined, this block will never be run again, okay? So this prevents recursive includes, this prevents, it just prevents recursive includes. However, for, again, the vast majority of cases, pragma once is sufficient. It's one line, it solves the problem, and again, unless you're doing some really esoteric stuff with the preprocessor, it's not it's not really critical to do anything but this. Oh, I don't know if I mentioned that, but this is C11. So that's what I'm using, C11. So I tidy these up because they have to be in order for me. And let me just compile that, make sure that works. It runs. Okay, so let's, in our CMake list file, I added stir.c and stir.h. In Maine, I have some includes. We include stir.h. We have our test program. And this is going to churn, right? We're going to change this a lot as we go along. But for now, that's what we've got. And then we've got our new stir.h, which has the structure in it, it has our functions in it, and our new stir.c. Okay? And I'm going to add those, commit them. And I'm going to push that up. And I think for today's video, that will do it. So tomorrow, again, based on feedback and, I'll take that into account. But I think what we'll do is, we've got strings. We'll work on, what will we work on? We'll enhance strings so that we can kind of deal with them a little bit more flexibly and not necessarily have to clone C strings all the time. And we'll get that kind of tidied up. And then I think we'll work on the next thing. I think most important thing would be like getting the state machine built. We've done that several times. We've done it in assembly language twice. We did it once in Rust. We'll do it in C. And because that's going to be a pivotal part of the game engine. And I also think we will build the state engine, and then we'll also build the actor system, because we're going to need that. And we've kind of, again, we've experimented with that in several different forms. So we'll build that. Again, those are going to follow the same pattern as what we've done with strings. We're going to have a module, we're going to have structs and a header file, we're going to have functions that operate on them. That's basically the pattern that we're going to repeat here on a lot of this stuff. So that's what we're going to do tomorrow. And we'll just keep going until we get Donkey Kong. We'll get Mario jumping and dodging, flaming barrels and pounding his hammer and killing that monkey. So yeah. Anyway, I hope this was helpful. And again, this is all YouTube only. So please, if you have questions or comments and you don't typically watch my Twitch stream, I guess let me pitch that. So I kept saying stream and feedback. So I have this Twitch stream. It's my Twitch channel is twitch.tv/nybbles.io, NYBBLESIO. So if you've seen this and you would like to participate in my streams, which run from 5 a.m. to 10 a.m. Mountain Time, Monday through Saturday, feel free to drop by. Otherwise, leave a comment here on YouTube. I certainly will keep track of comments and I will answer them, and I'll try to incorporate any feedback on this series. I don't have a definitive length for this series. I'm just going to go until the game works, and and until I've answered everybody's questions, because this is intended to be a tutorial on C, right? So I may have to recover some territory a couple times here and there to make sure that everybody is getting all the information they need. But yeah, so that's the plan. Feel free to drop by on my stream. I would really appreciate it if you would subscribe if you're new. If this is the first video you've seen of mine and you liked it on YouTube, please subscribe. Please click the little bell icon. Do everything that YouTube needs you to do to make it known that you appreciate my stuff. And I will see you in the next video. Thank you all. Goodbye.